Hello, this is the next video in a playlist titled General Linear Models, Design of Experiments. And this is part 6 of a little 10-part mini-series on one-way fixed effects ANOVA. And here we're going to look at the modifications in the unbalanced case. Up until this point, we've only examined what's called the balanced case. Now, it's when the number of measurements on the response is different for each treatment, the design is said to be unbalanced. So if we have 3 treatment groups and they all have a sample size of 10 in each treatment group, that's called a balanced case. Unbalanced means they're different, so it might be 8, 9, and 13 in each of the treatment groups respectively, and then that would be an unbalanced case. And so you write the model as this, Yij, it's still the same model here. So there's a grand mean plus some treatment effect parameter, error term. There's A treatment groups, but the number of observations in a treatment group varies, and we just call it Ni. So this is the number, but it depends upon what treatment group you're in. Now, modifications, and we'll go through these just relatively quickly. So capital N generally represents the overall sample size. In the balanced case, it's N times A, because the A groups all have N observations, so this is the total sample size. In the unbalanced case, we have to add the sample sizes for each treatment group. The M, which is the perpendicular projection matrix onto the column space of X, in the balanced case, it was a block diagonal of 1 over n times mu. And this, the U is a n by n matrix of all ones. So then this becomes an n by n matrix of all, constant 1 over n and block diagonal. In the unbalanced case, each block is a different size. Here, each little block is, n by n, it goes down. But this one, the block size depends upon the treatment size. J, which is the perpendicular projection matrix onto the column space of the 1 vector, is in the balanced case, it's this. So it's an NA by NA matrix of 1s and then divided by NA. Here, the dimensions is capital N by capital N, which is, NA is capital N in the balanced case. And so it's similar there. The treatment mean vector is in the balanced case. The treatment mean is repeated n times for each treatment effect, but in the unbalanced case, how many times it repeats is based on the sample size for that treatment group. So Y1 dot bar is repeated n1 times. The 8th treatment group mean YA dot bar is repeated NA times. Grand mean is just the overall mean times a 1 vector. For unbalanced case, it's still the grand mean times the 1 vector of length n. The degrees of freedom in the balanced case is NA minus A. In the unbalanced, it's capital N minus A, where capital N was the sum of the NI's. Total degrees of freedom is the NA minus 1 and N minus 1 in the unbalanced case. The constraints, sometimes called a side constraint on the towels, if that's the type of design that you wanted. In the balanced case, we just required that the sum of the TI's be 0. But in the unbalanced case, we have to take the sum of the NI-TI. So it's the treatment effect times the sample size. That has to be 0 in the unbalanced case. No treatment effect is that the tau i's, the treatment effects, are all equal to some grand mean value. This is for all I. And in the unbalanced case, it's also true that the tau i's, for no treatment effect, the tau i's have to equal some overall grand mean. But the grand mean is this. Remember that each treatment group has a different number of observations, so it's actually what's called a weighted mean. And this is for, and it has, for all I, this has to be true. No treatment effect. Oh, this is with the, without, no constraint, with the constraint, in the same way over here. I think I missed that part. This is without the constraint, with the constraint. And if that makes no sense, what I'm saying, no constraint, with the constraint, you have to kind of go back and look at the first few parts of this little mini series. The confidence interval for the treatment effect, I'm going to point you to part 5 for the balanced case. The unbalanced case is we just use the sample sizes for the treatment means, where in the balance it's just n, because they're the same sample size for each treatment group. And here, if you look at the difference of means, really it just plays a part here where you're factoring in the sample sizes for the ith and kth treatment group. Now, the advantages of a balanced case are that the procedures are more powerful, and they're actually more robust to small departures in the constant variance assumption of the epsilon terms. All right, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.